Hi everyone, I'm Jiaqi. I'm currently a postdoc researcher at UC Berkeley at Science Institute. I was a PhD student here at University of Maryland. So actually most of work here that I'm going to talk about today were done here at University of Maryland. So I'm very excited to talk about this series of works that are very interesting from both the perspective of physicists and also computer scientists. So the problem that I'm going to focus today. Oh, louder. Maybe
Is the microphone?
Yeah.
Do you turn it on?
Hello. Better. Okay. Great. So the problem that I'm going to focus today is this continuous optimization problem, which I just take the simplest formulation. We consider a continuous function over the whole Euclidean space, and we want to find the global minimum and the minimizer of this function. This problem has a lot of applications in virtually all computational and quantitative sciences, including machine learning, scientific computing, operations research, robotics, financial engineering, etc., as long as you can see. But this problem turned out to be a very difficult task for both classical and quantum applications, because many of the problems here are nonconvex, so which means the problem is hard. And sometimes we have really large-scale problems. And for many algorithms, including both quantum and classical, they have poor scalability. And also, many times we have precision issues that impede us to find a good solution. So for classical methods, for this type of continuous optimization problems, the most widely used classical algorithms are iterative search. Like many of the very famous algorithms, such as gradient descent, stochastic gradient descent, Newton's method, like the second-order methods, all of those algorithms were formulated as an iterative process in which you have a series of updates, and in each updates you just do something simple. For example, here I just give you a quick illustration of how like a typical iterative search algorithm works. You start from an initial guess. Usually we call this x0, and then you have some sort of directions guiding this search process. And then by iteratively doing this kind of updates, you find some like approximate solution in the end. And hopefully this solution gives you some useful information about the global or local minimizer of this problem. So the advantage of this kind of iterative search strategy is that they usually are very simple to implement. As you may know, that now we have some very powerful infrastructures like PyTorch that can be used to train very large-scale neural networks. And those are also very good local search strategies, which means you have very fast local convergence performance. But the disadvantages are usually, the biggest disadvantage here is that this strategy is very bad at finding global solutions to the optimization problems, which are very crucial in many applications in practice. For example, here, if I give you a non-convex optimization problem in which you have more than one local minima, in this case, if you happen to start from a very bad initial guess, and then you do this iterative search, and then you'll get a suboptimal solution, which is, again, a local solution, but it's nothing close to the global minima. And in this case, it's not very successful because you're not able to find the global solution. So our question here now is, how can we actually make this whole idea like quantum so we can leverage the power of quantum computers to accelerate or give us like better solutions for this whole problem? Like the very standard idea or the so-called conventional wisdom here is that we just replace some existing classical algorithm steps in those classical algorithms by quantum steps. For example, here, if we think about this classical iterative search, maybe we can just replace this each update steps with some quantum subroutines. For example, you can think about like quantum linear system solvers for a Newton method, or either even this linear combination of unitaries to give you like faster additive updates or something. But the problem here is that not all the classical parts in those classical algorithms can be sped up using quantum, because quantum algorithms are kind of like a limited subset of all the algorithms we know, and we don't have a lot of known quantum subroutines that can give you probable quantum speedups. And another even more serious issue here is, even if we can speed up this classical iterative research, the trajectory is still pretty classical, which means if you happen to start from a bad initial guess, even using this quantum computer, you cannot find a good global solution. You just make this whole process asymptotically faster. So That's the major motivation here. And in our work, we try not to replace each classical component by quantum algorithms, but we just try to quantize the whole search process. So in this whole idea, and this new idea, the iterative search process is lifted to a unitary map or the quantum evolution. So in this case, this is some process that we can efficiently implement using a quantum computer. So in this plot, I just try to give you a brief idea of how this idea works conceptually. Instead of using some classical point as our initial guess, we start from quantum wave functions. And then the wave functions involve in the whole continuous space. And then this objective function, that is our problem, effectively becomes the potential field in this quantum evolution system. And then through this time evolution, this wave function hopefully can find a better solution through quantum tunneling, and hopefully that will end up with a better global solution. That is what we want to find. And because of this quantum tunneling effect, we do have better hope to escape from local minima. So in that case, we can find the global solution or an approximate global solution. So here I want to give you some more technical details on how we achieve this. So for this standard classical gradient algorithms, the first step is that we try to formulate it as some sort of physical processes. Here we borrow the idea from this Pinus paper by Wibisona, Wilson, and Jordan in 2016. They showed us for some classical accelerated gradient descent algorithms. So here in particular, this Nesterov's accelerated gradient descent, we can use a Lagrangian mechanical model or Lagrangian to formulate this optimization algorithm as a quantum process. And equivalently, we can also put down this Hamiltonian formulation, which is mathematically equivalent to this Lagrangian formulation. So basically, you have a time-dependent Lagrangian with this kinetic energy and this potential energy. And that's how the idea works. And the second step is, starting from this classical Lagrangian mechanics, we then using the path integral formulation of quantum mechanics due to Feynman to try to make this whole process quantum. So starting from this classical Lagrangian with this time-dependent kinetic and potential energy, we plug it into Feynman's famous framework using the path integral, and then we end up with a time-dependent quantum Hamiltonian operator, which turned out to be an unbounded operator with this quantum kinetic energy and this quantum potential energy. Both are time-dependent. And now we have another new dynamical system, which describes the evolution of a quantum particle, which is derived or motivated from this classical gradient descent. But later I'll show you, it actually show you exhibit very different behaviors compared to those classical counterparts. So we give a name for this new family of quantum Hamiltonian dynamics. We call it quantum Hamiltonian descent. And in this general framework, we can have more choices for these time-dependent parameters. In the previous case, we only have these time-dependent parameters motivated from the Nesterov's accelerated gradient descent. So we have 1 over t cubed and t cubed. But in general, we can have much more freedom in choosing those time-dependent parameters. And this is like what the general word quantum Hamiltonian descent refers to. And here I also give you like a brief pseudocode for how this algorithm works on a real quantum computer. Again, you start with some initial state that's like a wave function, but not a classical point. And then you evolve the Schrodinger equation according to this time-dependent Hamiltonian, which were derived from this quantization process. And then at some point, you stop the evolution, and then you measure the final state, the final wave function, using the position observable, quadrature observable, x hat. And then, later I'll show you some plot. And at this point, this wave function is usually very highly concentrated and clustered around the global minimizer. So in that case, we have a very high chance to get an approximate minimizer of this function. And the quality of that minimizer is usually very good because of this quantum tunneling effect. So I also want to briefly discuss about the physics of how this quantum dynamical system works, because I think the majority of the audience are actually coming from the more like physics community. So in the physics terminology, the quantum Hamiltonian descent basically is a quantum dynamical system with some damping. And here the damping terms, which is like the ratio between these two time-dependent parameters are converging to 0, which means in the long term, we have no kinetic energy in the system, while only the position energy remains there. And we have more choices for the time-dependent parameters because each of the choice of time-dependent parameters correspond to a different classical gradient descent algorithm. And also, this energy damping mechanism allows us to identify the low energy manifold of this full quantum Hamiltonian, which happen to correspond to the low energy configuration of the objective function. That is, we try to minimize this objective function. And also, another way to think about this idea is that you can actually interpret this as a quantum habitable method, because in this case, we can actually formulate the effective Planck constant for this whole physical system, which is, again, the ratio of these two time-dependent parameters. And as the time evolves, this effective Planck constant actually is converging to zero, which means you're getting a more and more classical particle, starting from a very quantum mode and then converging to like a semi-classical or even classical sense. So in that case, you have like a squeezing wave function, which basically means the particle becomes more and more tangible in the classical sense. And then in that case, you're basically having like a evolving quantum particle, which becomes heavier and heavier over time. Okay, and then now I want to show you some theoretical results that I promised to show you. This is not just a heuristic algorithm. So for convex problems, we're able to reproduce the same convergence rate as in the classical setting. So this is the theorem proven by Webison, Worth, and Jordan in 2016. They show that given these nice choices of parameters and then consider this classical Hamiltonian, you have this nice convergence rate for the convex f. And this convergence rate is controlled by this beta t function, which is one time-dependent parameters in the Hamiltonian here. We can show that actually using our quantum Hamiltonian with the same choices of parameters and the same assumptions, we can also show the convergence to the global minimizer of this convex function at exactly the same rate, because it's also controlled by this beta t parameter. The proof here uses this Lyapunov function approach, which is very new in terms of the quantum computing or quantum algorithm literature, because most of the existing theoretical argument to show the convergence for optimization algorithms here in quantum uses this quantum adiabatic theorem or this type of idea. But here we use this energy reduction idea directly to prove the convergence. For non-convex problems, QHD just show you radically different behaviors compared to classical. For example, here I want to illustrate like the performance or the behavior of QHD on this wave function, which is a very non-convex optimization problem. So here I have two rows of like plots. The first row of plots show you like the evolution of this quantum wave function over time, and each dot here represents like a sample drawn from this quantum wave function. And the second row show you these like the performance of this classical Nesterov accelerated gradient descent algorithm, and each dot represents the current point of an initial guess. And as you can see, over time, or in the classical sense, after some iterations, those dots in the classical algorithm, they clustered into those local minima, which are spread over the whole search space. But for this quantum algorithm, even though we have a slightly slower convergence rate compared to classical, these wave functions do converge to the single and unique global minimizer, which is pretty different from the classical performance. And also here, I want to show you the wave packet in this evolution, which looks more intuitive. As you can see in the beginning, the wave packet is very oscillatory, which is not surprising because we have a large kinetic energy in the beginning. And then as we evolve the quantum system with the energy damping mechanism, over time, we see this wave function becomes more like a direct delta-like distribution centered at around the global minimizer of this function. And then that gives you this whole idea of quantum Hamiltonian descent. Okay, and then we are also able to prove like a quantum classical performance separation here using this mechanism. So the idea is that we are able to construct a family of optimization instances. Those instances are very hard problems for classical because they have exponential number of local minima. For example, this family is indexed by the parameter d, which is the dimension. And for a d-dimensional instance, it has 2 to the d number of local minima. And we're able to show that QHD can produce an approximate solution to this each such a optimization instance in polynomial time and polynomial queries. And those polynomials are not very large polynomials, just cube in dimension. And in terms of gate complexity, it's d to the fourth. So that means given this exponential number of local minima, this quantum algorithm QHD can still find the global solution in polynomial time, which is pretty surprising because, like non-convex optimization problems, the worst case are NP hard. So those are definitely not very easy tasks for classical to do. And the key idea behind this theorem is that this quantum Hamiltonian operator is rotationally invariant, which means if you can somehow hide the global minimizer information using some sort of rotation, but this rotation does not really affect how QHD as a quantum algorithm to see this whole optimization landscape. But this rotation can easily fool classical optimizers, and you're not able to find the global minimizer after this rotation. And even though our proof strategy relies on the adiabatic theorem for now, but our numerical experiments show that QHD also works, even for this type of hard instances in the non-adiabatic regime, which means you can start with something that is not in the ground energy subspace, but eventually end up, it still converges to the global minimizer or some approximate global minimizer. And here I want to show you how classical optimizers behaves on this problem. So here we use the performance metric, which is called time to solution or TTS. Like the operational meaning for the TTS is the time required for a solver to find a global solution with at least 99% of success probability. And our experiment shows that all the classical optimizers that we tested, ranging from interpolation method, this is also like some sort of interpolation method, to first order methods such as stochastic gradient descent, and also some annealing-based algorithms such as dual annealing, Bayesian hopping. Those are like variants of simulated annealing, and also this global search based on the Groby branch and bound kind of strategy. All the classical optimizers give us like some sort of exponential scalings in terms of the TTS, which are considered to be large separations, performance separations between quantum and classical. And also, I want to answer a very interesting question, that is it possible to actually quantize this QHD? Because here, eventually we only try to measure this quantum system using the position quadrature, but not the full wave function. So it sounds like the input is low dimensional and the output is also low dimensional, and there might be a chance that we can somehow dequantize this whole process without using a full quantum computer. But the short answer is, of course, no. We do have some pieces of evidence. So first, we can show that QHD can solve a structured search problem, which is some sort of variance of the unstructured search. But here we have some extra structures here to match the QHD algorithm structure. So for this type of structured search problems, QHD can solve this problem with the query complexity, the square root of a capital N, where N capital N is the system size or the problem size. However, this problem has a non-classical query lower bound, which is linear in the problem size. So these already give us a quadratic query separation. That means, of course, assuming that you have only access to the classical computer, you're not able to reproduce this quadratic speed up. And a recent work, which is like a joint work between some folks here at UMD and me, we showed that this simulating this Schrodinger dynamics itself is BQP hard. Even though this sounds like very trivial, but actually when you try to do the proof, it's actually not that trivial as you think. Because this Schrodinger dynamics is also kind of restricted. You have this very standard kinetic energy and with a scalar potential field, which is pretty different from the usual like d-local Hamiltonians considered in condensed matter physics. So to prove this statement, it does require a series of reductions. But we're able to prove this. Basically, that means to simulate this dynamics, you do need a quantum computer. And also, QHD may inspire new algorithms that are just suitable for classical computings, because even for these classical Hamiltonian systems, they do exhibit some interesting behaviors, such as chaotic behaviors, even though those are not quantum tunneling, but they may give you some other sources of like randomness in this whole system that may be able to help us to better explore the optimization landscape. Okay, and now I want to spend the last few minutes to talk about the implementation of this quantum Hamiltonian descent algorithm. Can we implement QHD using quantum circuits? Of course, yes, because this problem is just a time-dependent Hamiltonian simulation in the real space. And we do have polynomial time quantum algorithms. You can show that the asymptotic cost for simulating this quantum dynamics is linear in the evolution time and linear in problem dimensions, which matches actually what we have for the classical gradient descent. In gradient descent, the asymptotic cost is linear in the number of iterations and also linear in dimension. However, we did a resource count, and we find that if you try to follow this standard quantum circuit implementation, they require usually like billions of quantum gates, even without talking about fault tolerance. That's a lot, and we just cannot implement that in any near term. So maybe not in the next 1 year, but maybe in the next 5 or 10 years, who knows? But here, the short answer is, if we really want to do this now, in the next 1 year, or even just currently, we need to go beyond the gate model. So that's the next topic. That is, we want to consider implementing QHD using analog simulators. So analog computing basically means you use one Hamiltonian to simulate another one. I believe almost everyone is very familiar with this concept already. So here, I think QHD is a very nice target for analog simulation, because QHD itself is formulated as a Schrodinger equation, a tiny evolution of the Schrodinger equation. We have some other like quantum analog simulators that can also simulate some sort of Hamiltonian simulations. For example, here, this type of quantum Ising machine, or some sort of programmable transverse field Ising Hamiltonians. But the difficulty here seems to be that this Hamiltonian looks very different from this quantum Ising Hamiltonian. And we definitely need some sort of reduction or conversion between these two Hamiltonian models to be able to simulate this QHD efficiently using existing hardware. And that's the reason why we propose a new technique called Hamiltonian embedding, which is exclusively for simulating sparse Hamiltonians or sparse matrices using like existing and programmable quantum simulators. So using this Hamiltonian embedding idea, we are able to efficiently simulate QHD to solve nonlinear optimization problems. For example, quadratic programming using existing quantum hardware. And later, I'll actually show you we develop a software library that you can directly call to implement this whole process automatically. In this Hamiltonian embedding technique, the number of qubits is roughly proportional to the problem dimension, which means it's pretty scalable. You're not going to go exponentially in terms of problem dimension. The number of couplers depends on the nonlinearity in the problem. And even for some like simple nonlinear problems like quadratic, this is usually like quadratic, in the worst case, quadratic in problem dimension, but still like polynomially in problem dimensions. Evolution time seems to be polynomial in dimension and the couplers, but we do need better theoretical understandings for this whole process. And using this whole like pipeline, we're able to solve some 75-dimensional nonconvex quadratic programming problems using existing quantum hardware, that is D-Wave, and we use over 5,000 physical qubits to accomplish this whole like solution. Just a quick slide on how this Hamiltonian embedding works. Like in the traditional Hamiltonian complexity community, we also have a bunch of techniques that help us to reduce D-local Hamiltonians to 1 and 2 local Hamiltonians using the so-called perturbative gadgets technique, and that helps us to prove the universality of local Hamiltonians. Here, actually, our Hamiltonian embedding ideas are closely related to these perturbative gadgets and Hamiltonian complexity kind of ideas. But here we start with sparse matrices, which are more common, in computational sciences. And then we slightly change this, some sort of the elements in the perturbative gadgets, and then end up still with 1 and 2 local poly operators, which matches the analog simulator. So here, basically, this embedding not only preserves this Hamiltonian structure, the spectrum structure, but also it gives you some hint on a succinct basis change. And that's the major difference between the perturbative gadgets and our Hamiltonian embedding, because using perturbative gadgets, you only preserve the spectrum, but sometimes the rotation or the basis change is quite, it's not usually very transparent. So that's not something you can directly implement using a quantum computer in most cases. But in our case, we do have a succinct basis change, so that's something you can directly implement and read out from quantum hardware. And basically, the idea is we fix like a small subspace in the full Hilbert space. And then in this subspace, we can try to embed this target Hamiltonian, which are some sparse matrices, into this embedding subspace. And then this full similar Hamiltonian is split into the direct sum or approximately a direct sum of two Hamiltonians, one located in this embedding subspace, another in the orthogonal complement of this embedding subspace. And by evolving this full Hamiltonian, you're getting approximately the direct sum of two time evolution operators because those are approximately decoupled. And then by just measuring in this embedding subspace, you can recover a lot of information for this target or sparse Hamiltonian. And we do have a lot of applications for this technique beyond optimization. For example, we can do this for simulating quantum walks on graphs and also doing ODEs and PDEs. I think some of the folks in our group at UMD, they are also focusing on some of the future extensions of this technique. As I said, we also build a software library to directly implement QHD and map that to existing quantum hardware. For example, here we have this QHDOPT, which is a software library that we developed, and we target this type of nonlinear optimization problems. Those are just nonlinear optimization with box constraints. Here, all the variables are in this like a box or some sort of rectangular shape. And for the objective function, we have this univariate part, which you can imagine some sort of like linear-ish like function, and this bivariate part, which give you nonlinearity even in the simplest case. And this is the whole pipeline for this software. We leverage this SimuQ idea, actually credit to Yuxiang, which is like a high-level compiler that you can directly leverage to compile quantum Hamiltonians to the hardware. And our software library is available on GitHub, so you can scan the QR code. We're now testing our software with different groups in operations research and industrial engineering departments. And we're seeing some interesting and encouraging results, even apply this software to real practical cases. And we also try to make our software friendly to non-quantum computing experts. Because for many optimizers, they know math, but they don't know quantum physics that well. So we just make this a whole high-level input format kind of modeling, so they can directly use the language that they're familiar with to formulate the problem, and then our software will take care of everything. Okay, and finally, I want to show you the performance of our software, which implements this QHD algorithm to solve high-dimensional non-convex optimization problems. Here, we target this non-convex quadratic programming, which is to minimize this quadratic function with an indefinite Hessian matrix Q. This problem is known to be NP-hard. And again, we use this time-to-solution performance metric. As you can see here, our D-Wave implemented QHD has the best TTS among all the other tested solvers, including quantum and classical. Here, this D-Wave QAA is just the standard D-Wave implemented QAA, but we just use the naive Qubel encoding of this continuous problem. And this SNOPT and IPOPT, those are just standard optimization softwares leveraging interpol methods. And this TNC from SciPy library, MATLAB, we use the fminconv function. QCQP is a heuristic algorithm to solve non-convex quadratically constrained quadratic program problems. And all the other softwares that we use they demonstrate worse TTS compared to this quantum solution. So again, we use 600 digital qubits, but that amounts to over 5,000 physical qubits on the D-Wave quantum hardware. And this is a very strong evidence, just supporting us that QHD could be a very useful thing, even in practice. Okay. And finally, I just want to show you the summary of this whole talk. We have this new quantum algorithm, which is an upgrade of the classical gradient descent. And we do have some evidence, especially theoretical evidence, to show why this works and why this is not classically simulatable. This QHD admits both quantum and digital and analog implementations, especially if at the current stage, we think analog implementation is the better choice because we do have larger scale analog simulators. And then we're developing software toolchains. Now we already have something, and then we can continue this whole developmental pipeline. And we have a bunch of references here. All of them are available on arXiv. And this software paper was recently accepted by the Informs Journal on Computing, which is a top-tier journal in the operations research community. Yep, so if you have any questions, you can let me know. And thank you so much for your attention.
Any questions?
Yeah. Can you
show us your pseudocode again?
Oh, your pseudocode? Oh, sure.
It was very early. Yeah,
Oh, it's here.
you passed it.
Yeah. Oh, sorry. Yeah.
Yeah, there you go. Well, can you get, you write e to the phi t.
Yeah.
And e to the chi t.
Mm-hmm.
Can you give us a little better sense of how big or small those functions are? I mean, there's no information there.
Right.
So, I mean, what are those things?
Sure. Yeah. So on a high level speaking, this e to the phi t, which is the thing in front of the kinetic energy, should be some sort of a monotonically decreasing function.
From a high value?
From a high value to a low value. Usually, in our experiments, it's like around 10 to 100 numerical values. Yeah. But in our like theoretical formulations, in the numerical experiments I show you, we use this 1/t cubed function. But we start from a non-zero t, like a very small but non-zero t. So you have some 1 over a small number to the cube. And usually we start from something between 1 and 10, so you get something between like 10 to 100.
And then the next one?
The next one is usually the reciprocal of this.
Just the reciprocal.
Yeah, that works very well in practice. But I think in theory, you can also plug in some increasing functions. They do not necessarily need to be reciprocal to each other, but some increasing functions just to control the kinetic energy so that it doesn't drive the system in the long-term limit, so it will eventually stop at some point.
And what's the initial state?
The initial state for the quantum evolution?
Yeah.
Usually we just start from some easy to prepare initial state, for example, the uniform superposition or some Gaussian state, which has no information of the objective function.
Okay, thank you.
Yeah.
Thank you for the great talk. So you have assumption on for this algorithm to work on semi-classical limit, which is near when the gamma is much larger than phi, near the end of the evolution, the lowest n eigenstate of the target Hamiltonian is approximated by the quantum eigenstate, and this is somewhat a strong assumption. I wonder. Is there a easy way to check that this assumption hold? And also, you call it's called semi-classical, so it's a little bit counterintuitive that then you claim this cannot be dequantized. So can you remark on that?
Right. For your first question, that assumption by itself is very weak because in like function analysis or like mathematical analysis, you can actually prove that for some smooth f with a unique global minimizer, regardless of any other structures. And when this entering this semi-classical limit, which means the coefficient or the factor in front of the potential energy is much bigger than that in front of the kinetic energy, you always have a ground eigenstate that corresponds to or somehow is close to the direct delta function that's centered at the global minimizer. This always holds, regardless of whatever the structure, fancy structure is on the function f. But in terms of this quantum algorithm, the real challenge here is actually how you can stay within this low energy subspace all the time, because you're guaranteed to have a low energy subspace that give you information about the global minimizer. But here, the real problem is how you can actually make the whole quantum system stay within this low energy subspace. And that's the reason why in our proof, now we still try to use the simplified formulation, which is we try to stay within the ground energy subspace. And in our proof, we can show that there is actually a spectrum gap. So you can prove like this algorithm works in polynomial time. But numerically, we do observe that what actually happens is much weaker than what we can, much stronger than what we can prove. So in many cases, even though this spectrum gap is not that large or something, that the quantum wave functions still stay within this low energy subspace. And that's because maybe the spectrum of this quantum system is more complicated, and there are some intrinsic structures that we're not able to analyze using existing tools. Yeah, and as for your, can you repeat your second question again? I think there's another.
Yes, I think the second question is kind of answered also
Yeah.
because your assumption is similar to, in that sense, to adiabatic, except you want a gap not just between ground state and the first excited, but between lowest end state with all the higher states.
Right. That's still the strategy we use now. That's the strategy we use now. But as you can see from the convex analysis case, in that case, we have no assumption on the spectrum gap. it's unconditional convergence in the convex case. That's because if you see numerically, all the eigenfunctions eventually collapse to the global minima because the function is convex. So in that case, you don't even need to stay within the Lorentz subspace. As long as the energy is finite, you're able to converge to the unique local minima in that case. And I think that analysis can actually be extended to some non-convex cases. If that's possible, then you can just discard this adiabatic kind of assumption. Yeah.
Thank you.
I think we take one last quick question.
So to implement this, you had to embed it in a lower dimensional subspace, correct?
Right, yeah.
How do you find that subspace?
You mean like starting from this Lorentz subspace or something? Like
Yeah, how
interesting?
do you find the subspace to encode it in, or does it not matter which subspace? It has to be an invariant subspace, right?
Wait, you're talking about the Hamiltonian embedding, or like this just so this whole algorithm?
The no, the embedding part.
The embedding part.
Yeah.
Right. So in the embedding part, the Lorentz subspace should be, or the encoding subspace should be specified before we run this algorithm, and that's something we can theoretically prove it works. Which you can explicitly write down like a basis for that like embedding subspace. And in that case, you can easily prepare a state that that is within this subspace. For example, in our implementation of QHD, the uniform superposition state is actually in this embedding subspace, which means you can just start with the uniform superposition state, which you can it's probably in this embedding subspace, and then you evolve it, even though it does not look like exactly the uniform superposition state in the embedding subspace. But like you can check the linear algebra, still it's in that subspace. So that's something you can check and prove before you even run this algorithm and it work in practice.
All right, I think we should wrap for lunch. So let's thank
Yeah,
everyone
yeah.
one last time.
Thank you.